With the simple new proposal for lepton substructure now obtained, it is now time to take a look at the hadrons. In all of the high-energy physics experiments done over the last 50 years, it has been observed that any new elementary particle that has been found can be classified as either a lepton or a hadron, and it has been observed that the hadrons come in one of two types. There are baryons, which are proposed to be made up of 3 quarks, and there are mesons, which are proposed to be made up of a quark and an antiquark. In this slide, the delta family is shown as a representative baryon family. As can be seen, there are 4 possible ways to make a delta particle out of up and down quarks, and it is observed in nature that only these 4 particles are found. Shown below the delta family is the pion-meson family, which is a representative meson family. As can be seen, there are 4 ways to make pions out of up and down quark-antiquark pairs, and 3 pions have been found in nature. There is some evidence that the neutral pion is actually a superposition of 2 different types of quark substructure, as is shown in the diagram. Note that the overarching rule for making hadronic matter is that the total color of all particles must be white, and that one can obtain white particles in one of 2 ways. One can combine 3 primary colors, as in the case of the deltas, or one can combine a color with its anticolor, as is the case with the pions. Here we see why baryons are formed of 3 quarks, since that is how the 3-color combination can be achieved. And we can see why mesons must consist of quark-antiquark pairs, since that is how a color-anticolor combination of colors can be obtained. In addition to the delta and pion families shown here, there are many, many more similar families of particles found in nature. The quark model allows for a replacement of a down quark by a heavier strange quark or by an even heavier bottom quark. And it also allows for the up quark to be replaced by a heavier charm quark or by an even heavier top quark. It is easy to see that by making all of the permutations of such replacements, one would get an enormous number of particles. Of all particles found to date, there are none that fit outside of the quark, lepton, and force carrier model, and hence there is quite a good agreement between the experiment and theory for the present quark and lepton theory. We just saw how all known hadrons can be made from a model using quarks and antiquarks. However, there is another way that these particles can be made. Here we see that if we propose a new particle called C, and let the C particle be bound to 3 A particles or B particles, that we again will have only 4 possible ways to make a delta particle. By assigning an electric charge to the C particle of +2, the delta particle will have the possible charge states of +2, +1, 0, or -1, just as is found in nature. We can also see that the mesons can all be made if we allow a C particle to bind with its antiparticle, and then allow one remaining bond to either an A or B particle, depending upon the choice of particle. In this way, we can see that we can make up all of the known baryons and mesons just as easily as one can with the quark model. While at first it may seem that the arrangements shown on the previous slide are an arbitrary grouping, it can be shown that the groupings easily follow if we assign a neutronic charge of +3 to our new C particle. As was the case where leptons were analogous to the hydrogen atoms, we can now see that baryons are analogous to lithium atoms. In the lithium atom, a nucleus with an electric charge of +3 is orbited by 3 electrically negative electrons. In baryons, a C particle with a neutronic charge of +3 is orbited by 3 neutronically negative particles. Here I also show the binding neutrino for each binding. In this instance, I show a particle with electric charge of +1. Since the C particle has an electric charge of +2, the B particle has an electric charge of -1, and the A particles have 0 electric charge. Of course, as shown in the previous slide, we could have had 3 Bs, 3 As, or 2 Bs and an A orbiting around the C particle, and in those cases the electric charges are different from what is shown here. But the important point is that assigning a neutrinic charge of +3 to the C particle leads to a situation where all of the known delta particles can be formed, and no additional delta particles are possible. Hence, this new model is every bit as good as the quark model in predicting all of the known delta particles. As a last point, note that we have now introduced a new particle to the mix, which is an A particle with a -1 neutrinic charge. In the lepton case, we had an A particle with a +1 neutrinic charge. This new A particle is the antiparticle of the A particle that we saw earlier. At this point in our development, we can now make an identification between the ABC preons and quarks. Here we again see a depiction of the delta plus particle, but I have placed rectangles around some of the components. The rectangle drawn around the B particle, its binding neutrino, and a portion of the C particle, is recognized as a down quark. The rectangles drawn around the A particles, their binding neutrinos, and a portion of the C particle are recognized as up quarks. In this Preon model, quarks don't actually exist as particles. Instead, quarks are identified as a quantum state involving the orbiting A and B preons and the central C preon. As with leptons, this realization allows us to understand how generations of quarks come about in nature. The U and D quarks are the ground state of the system, while the strange quark is the first excited state of the orbiting B particle, and the bottom quark is the second excited state of the B particle. Similarly, the charm quark is the first excited state of the orbiting A particle, and the top quark is the second excited state. With mesons known to be composed of quark-antiquark pairs, we can now construct mesons in the ABC Preon model by taking the relevant preons and antipreons and combining them in a similar way. Here we see a pi meson that is modeled in the standard model as a U quark bound to an anti-D quark. In the ABC Preon model, the U quark was just seen in the previous slide to be the state composed of an A particle bound to a C particle, and that structure appears in the pi meson here as well. In the previous slide, a D quark was seen to be composed of a B particle bound to a C particle, and here we see that a D antiquark is composed of a B antiparticle bound to a C antiparticle. Since the C particle has a neutrinic charge of +3, and its antimatter partner has a neutrinic charge of -3, a double bond appears between the C particle and its antiparticle. Hence, a total of 3 bonds appear in the diagram for both the C particle and the C antiparticle. Note that I have introduced the standard notation for antiparticles in the diagram, where a bar appearing above the letter indicates an antiparticle. The double bond between the C particle and the C antiparticle is analogous to a situation found in chemistry, where it is known that atoms share electrons in the chemical binding. Here, binding neutrinos play the role that electrons play in chemistry. Each C particle and C antiparticle have 3 neutrino sites available for bonding, while the A and B particles and antiparticles have a single binding neutrino site. Note that in the model proposed here, quarks are identified as simply being a notation for a binding between C particles and either an A or B particle. While massive leptons can be isolated as an A antiparticle bound to a B particle, a quark can never be isolated by itself, since it is in reality the manifestation of a portion of a C particle bound to an A or a B. This is why free quarks have never been observed. Finally, note that in all of the modeling we have done so far, the rule has been that particles found in nature are those that have 0 neutrinic charge. This fact was true for the modeling of the massive leptons, and it is also true for modeling of baryons and mesons.